to the, hello everyone, thanks for coming to the dissertation proposal of Mingrui Zhang. I'm very excited to see Ray's presentation today. And I'm glad you're here to see the same. The committee is myself, Jacob Wobrock as chair, Alexis Hineker as University of Washington Information School, Leah Finlater as from the University of Washington Department of Human-Centered Design and Engineering, and Shuman Jai as our external member from Google. James Fogarty from Computer Science at the University of Washington is our graduate school representative, also known as the GSR. James, as a reminder, your role is to make sure our examination is both rigorous and fair to the candidate. So we will spend the first 40 or so minutes, I think, 45 maybe, on Ray's giving us a presentation of his work and his proposed work. And then we will move into a general Q&A session where we will alternate, doesn't have to be strict alternation, but roughly alternate between the committee and the general audience. After that point in time, we will seclude with Ray as the candidate and the committee to ask further questions. And then we'll ask Ray to step out. The committee will confer, and then we will come back and give Ray our decision. So that's the general outline of the steps. Are there any questions or preliminaries before we begin with Ray's dissertation proposal presentation? Okay, hearing none, I will assume that everyone's clear on what we're doing. And I think that means it's over to you, Ray.
Okay, let me share my screen first. All right, can everyone see my screen? Great. Hi, welcome to my proposal presentation, Intelligent Text Input Methods and Metrics. My name is Mingrui Zhang, and I'm a fourth-year PhD student here at iSchool, UW. My committee member is Jacob Wobrock, Alexis Hineker, Leah Finlater, Shuman Jai, and James Fogarty. So first bit about myself, I come from a computer science background. In my PhD, I conduct research in human-computer interaction, specifically in language production and text-related interactions. And in my spare time, I like playing video games. Okay, that's not really related to this talk. So what do you see on this screen? Nothing. If there's no text, we barely have any information. So text is really important. We talk, we read, we write, we even think through text. Text is the medium of information. So the interaction of input text is also a foundation part of any human computer systems. We write text to program, to search things online, to chat with each other, and also to write our proposal. So my research is then to design and evaluate text input systems. This research direction has a long history because it's pretty hard. And in my proposal dissertation, I say language specifically to English language. So why is it hard? There are three difficulties. The first one is human language is just complex. There are 26 characters in the English alphabet. And if we are talking about typing, we need to assign 10 fingers to map those 26 characters, which cause ambiguity. And there are so many similar words in the English language. And if someone types them to each other, the system can have a hard time to recognize whether it's wrong or right. And thirdly, there are no rigid rules in language. Every day there are new memes or words coming up, and the keyboard needs to update constantly to offer a better experience. And the second difficulty is when we talk about text input, it's not only about entering letters. There are also editing process like delete, remove, correction, and also special characters like punctuations and emojis. And thirdly, there are so many interfaces around us. We need to incorporate from traditional keyboard to touchscreen to even no explicit input device like VR or AR headset. And so many form factors we need to incorporate. So let's have a review of the popular input techniques so far. And on the left, that's a first successful commercially typewriter, Scholz and Linden typewriter. And since then, the quadric keyboard layout have become the standard layout in keyboard. And later on, there are other alternative layout like this Dvorak layout invented by a professor here at UW, and other layout like for touchscreen, numpad keyboard, and new interactions like gesture typing invented by Shuming, and this add write for accessibility invented by Warburg, my advisor. And there are so many more. However, there are three common limitations among those devices or projects. The first one is they operate on character level or word level. That's a tool for output literal strings, but they do not understand what the users are thinking. And the second one is their learning curves are too steep, meaning that the user needs to take a long time to master the device. And thirdly, a lot of this project only considering the entering part without like editing or special punctuation. So my research question is, first, then how can text input systems understand the user intention? Of course, the end goal of text input is to communicate your thoughts. If the keyboard understands your intention on a higher level, like meaning, then the text entry system will be more efficient. And the second is how to design intuitive, low-effort text input interactions, including entry, editing, and symbols. And the third question is, with those new input techniques, how to evaluate those novel input systems. My approach is then to use the power of artificial intelligence, not this figure, artificial intelligence. So specifically, I use neural networks to incorporate larger context from the input and to understand the user on the semantic level. And I use machine learning algorithms to recognize gesture and actions to design more intuitive interaction. And thirdly, I derive metrics and models for those systems. So the first chapter of my work is about designing intelligent text input methods. First, I like to introduce a keyboard called FreezeFlow. It's a phrase level input method. So I think we all got these awkward moments where autocorrection has corrected the text into wrong word. Part of the reason is that autocorrection operates on the word level. So each time you press space, the word before the space gets corrected and fixed, no matter what text you type later on. In this example, the user wants to type, "I live in Seattle," but because the space bar is pressed, love is fixed on that correction. And we human can spot the error easily based on the later context in Seattle. So a natural idea is, can we make the keyboard not only consider the previous text when correcting a word, but also the text after it? In this work, I invented a phrase level keyboard, and it delays the correction until further information. In this example, until the keyboard says "in Seattle," it will then correct the love into live, which makes more sense. So let's have a look at the demonstration.
We present FreezeFlow, a phrase-level input keyboard designed for daily use. We systematically explored different interaction aspects of FreezeFlow, including correction effects, text markers, commit methods, and more. Specifically, we designed the buffer commit method, which only commits the first word of the text after hitting a space, instead of committing the whole text at once. Phrase level input can utilize the subsequently input sequences, including the space key, to correct the previous.
Oops. So I want to mention here, as you can see, that the underline implies that the whole phrase is being corrected right now, and versus the word level one, it's already corrected every time you press space. So even you press space, it's
By
continuing.
utilizing the future context, it reaches better correction performance than the current word level corrections.
Okay, that's a famous phrase. So that's an introduction. I want to briefly talk about how I implement the phrase level correction. The keyboard is using a state machine called finite state transducers for auto correction, FST. FST has two elements. The first one is states, circle here, and the second one is transitions, arrows here. So when you type a word, say like if, the keyboard will transit from state 1 to 2 when you type I, and then go to state 3 when you type F. And when it sees a space key, it will go back to the initial state and correct it if there is auto correction. So what I did is I disabled this transition to make the keyboard continuously correcting the whole phrase. For this project, I conducted 7 user studies with 2 in-lab evaluation and a field deployment with 46 participants. And the results show that phrase level correction reduced the error by 16%. And users performed better with phrase flow. And in the field deployment, more than 78% of the user prefer this correction, and they would like to use it in their future keyboard. So that's the input part. And next, I would like to shift the focus into text editing interactions. The second project, Jetted, is a set of keyboard gestures for mobile text editing. So suppose you just realize a correction mistake before sending the message. What will you do to correct it? Current practice is you move the cursor and you delete it. But it can be imprecise, and if we want to trigger more editing options, we need to hold down for a few more seconds. Some keyboards offer editing options on the keyboard itself. However, they either need to clutching several times if you want to move the cursor further away, and also the lack of single hand support. More importantly, if you are doing gesture typing, they are not compatible because they use gesture. So to address those limitations, I designed Jetted, a set of on-keyboard gestures similar to the keyboard shortcuts. So this is a demo of I use Jetted. And you can see I use a circle-like gesture to select text, and then perform gesture to cut, paste. With the ring-like gesture, you can move the cursor infinitely without clunching. And there are some like convenient gestures for cursor moving. So there's a editing mode where if you swipe from the edge to the from the screen, you will enter that mode, and you can do some special editing options like text selection if you move the gesture, move the cursor. And then you can draw characters like C or X or V for copy, paste, and cut. And then there's a one-hand edit mode where if you initiate the gesture from the edge, you can just do it in one hand. And also the gestures are compatible with gesture typing because only gestures initiated from the spacebar will be recognized for cursor control. So for the gesture recognition, I used a $P gesture recognizer to implement the editing commands. And the last project in this chapter is about improving the text correction process, where I introduce a new concept called type then correct, together with 3 accompanying interactions. Again, back to that example. Like I said, traditionally, we will move the cursor back and delete the error and retype the correction again to correct this single error. And that's just too many steps. Can we improve this? So instead of locate the error first, can we type the correction first and then apply it to the error? Another demo.
Time to show our new correction interactions. Drag and drop. Type the correction at the end. Drag it to the error place and drop it to substitute the error. You can also insert a correction by dropping on a space. Drag and throw. First, type the correction. Drag the correction from the suggestion list and throw it to the error text. Then our deep learning algorithm will figure out how to apply the correction. It can also handle insertion corrections. Magic key. After typing the correction, tap the magic key to highlight a possible error. Tap the key again to apply the correction. Insert corrections as well. With magic key, you can just keep typing without leaving the keyboard area. This preserves the typing flow.
So the intelligent interactions just introduced with drag and throw and magic key need to locate the errors given a correction. And to do this, I use the neural network model with the encoder and decoder part to identify what are the potential errors. As a side note, the text and then correct project has inspired researchers outside UW to carry on the work of improving the correction interaction, resulting in a new technique called just correct. In this chapter, I demonstrate how artificial intelligence can empower the text input system to incorporate higher level context into the entry and editing process.
Okay, that's pretty interesting presentation so far. I have a quick question. So, when people try to interact with others, they not only use text, but they also use, for example, emojis. Yeah. Do you have any ideas on how to improve that?
Sure, that's exactly what I'm going to do in the next chapter. So in this chapter, I present my work about designing intelligent emoji input methods. The first one is an empirical study on comparing different emoji suggestion systems. As we all know, everyone loves emoji. There are currently more than 3,000 emojis available on your keyboard. However, the input of emojis are not so satisfying. The common way is to select manually from a range of options in a list. And some keyboard, you can do search. So the suggestion mechanism really is the input process. One kind is lexical-based emoji input, where you type a keyword and there will be a suggestion like a bear emoji. And the other kind is semantic-based suggestion mechanism, where it input the whole phrase for suggestion and give back you semantically related emojis on the whole phrase. A difference can be seen in this example. If you type, "I enjoy the fish tonight very much," the lexical will output like fish emoji or tonight related emojis, but the semantic one will output like enjoy faces or hungry faces because of the expression. However, although this suggestion mechanism can make the input of emoji more efficient, we do not know whether they can affect our chatting experience. Like, maybe they will encourage us to engage more or chat more often. So to investigate this question, I implement a keyboard with two suggestion mechanisms. The left one is word-based, where you type a word, it will suggest all the emojis related to that keyword. And the right one is semantically based, where you type a phrase, I will use a neural language model to predict some related emojis based on the phrase expression. And to investigate the problem, I conducted two studies. The first one is an in-lab study where I have pairs of strangers chatting in separate places with different keyboard. And the second study is it's a deployment study where I installed the keyboard with different suggestions on people's phone and let them use for 15 days. For both methods, I logged the total characters, the total emojis, the selected emojis from the suggestion list, and also their subjective rating on the online chatting experience. A little surprising thing is there is no significant difference between those two groups. So basically meaning that it is the emoji rather than the emoji suggestion mechanism that's affecting your online chatting experience. However, we do find that people select more semantic related emojis than the lexical one. We also found that people like both emoji suggestions for different reasons. People like lexical ones for they sometimes providing more unusual or surprising emojis, and that was fun. And people like phrase level, semantic level suggestions because sometimes they can get a clue of their connotation and their language style from the suggestion. So having looked at emoji suggestions, I then revisited the input problem of the emoji. And in this time, I designed an emoji entry system for accessibility issues. Voice emoji is a speech-based input system for visually impaired users. It can be a little bit surprising, but people with visual impairment also use emoji a lot. But the current experience can be quite tedious. This is an example of how a blind user input emoji. He's using a screen reader for feedback so that he can interact with the mobile phone.
Next category,
And
button.
I won't speak, but I will swipe through the emojis in this category, and hopefully you'll be able to hear how VoiceOver describes those emojis. And hopefully I will find the calendar emoji.
Objects, Minisk, 842.
That's very retro.
Floppy disk, 843.
That's positively 90s.
CD, 844.
So basically, he just swiped through this list linearly to listen to every emoji. So that's certainly very slow. And based on our interview, we found that the common challenge is it's very slow to input emojis for our user. And also sometimes it can be very inconsistent because sometimes you have to guess where the emoji is. For example, if you want to input a white cane emoji, you may go to the object category, but it's actually in the vehicle category. And the last point is the current methods offers limited support for exploration and learning new emojis. So this is a demo for voice emoji.
Voice Emoji is a speech-based emoji entry system for blind or low vision users. It has 4 main functions. Searching emojis by saying emoji search plus the emoji keyword. Emoji search, rainy day emoji.
Possible emojis are first emoji cloud with rain emoji, second umbrella with raindrops emoji, third emoji sun behind cloud with rain emoji, fourth emoji cloud with snow emoji, fifth thundercloud and rain emoji. More available. Emoji sun behind cloud with rain emoji. Added emoji sun behind cloud with rain emoji.
Context-sensitive emoji suggestions based on the spoken context. I'm going to play the guitar in the music band.
I'm going to play the guitar in the music band. Emoji suggestions available. emoji peace hand sign emoji, emoji postal horn, emoji guitar emoji, button, emoji added emoji guitar emoji.
So there are other like minor features, but basically those are the
Voice
two main
emoji is a
features, two main features. The first one is support natural language style for emoji search. To do this, we send the query to a search engine and gather the result, return and extract related emojis in the web page. And for emoji suggestions, we use methods from the previous study for suggestion mechanism, and also suggest like word and also semantic level results. And this also helps the user to learn about new emojis. I conducted 2 online studies with people from China and also in US. And on average, the entry time was reduced by 90%, over 90% with voice emoji compared to the iOS keyboard. And also all the suggestions are perceived as very relevant. So as new interactions are invented, it's also important to evaluate their performance. In this chapter, I will cover my work on deriving new model and metrics for text entry. I first present the transcription sequence model for evaluating text error rate. Speaking of the performance, we will think about text speed and also accuracy. While speed, we use word per minute to evaluate. There are many error rates for accuracy, including the errors that are corrected during the typing process and the errors that are not corrected. While the speed is straightforward to measure, the errors are a little bit complicated. And in fact, before 2000, all the text entry evaluation tasks won't allow user to make errors or won't allow them to correct. As you can see, there is no correct or backspace in this interface. So later on, an evaluation model called input stream model came out and enabled the user to make backspace during the typing. So usually for a text evaluation, there will be a present string shown to the user, and the user are told to type the transcribed string as fast or as accurately as possible. With the input stream model, we can reconstruct the user's typing flow. For example, here, with the present string shown here, from the input stream, we can know that the user first type read and then delete the 3 characters and then type the rest of the string. However, the limitation of input stream is that it only allows the text modification happen at the end of the text, and it won't handle where the text change happen during, between, or in the middle of the text, where if we are using like auto correction or copy paste, they can modify text anywhere. So the transcription sequence model solves the issue by taking snapshots of the transcribed text every time it changes. I also designed a string comparison algorithm where it can compare the neighboring sequence and reconstruct the whole dynamic process. In this way, the errors happen during typing can be recovered and calculated. And with this model, the user can use many more than text features during the evaluation and using more realistic results. Okay, so now we can measure error rate with the new model. Yeah, but is it enough to use only speed and accuracy as the metric? Here comes to the throughput metrics, where I aim to derive a metric on the overall performance level. Speed and accuracy represent different aspects of performance. However, how do you compare if one keyboard has more accuracy but low speed versus the other keyboard is faster but more error prone? Moreover, humans have innate speed accuracy trade-offs. You type faster, you make more errors, and vice versa. So the goal of this project is to find a performance metric that combines the information from speed and accuracy and overcomes the speed accuracy trade-off, which means it should be constant for the same person with the same method, even they are in different speed accuracy conditions. And that metric is called text input throughput, text entry throughput. Throughput is inspired by the information theory. It's used to measure the information transmission rate of a communication system. And we can think the text entry process at the communication system, where the present string is source, the transcribed string is the destination, and we human plus the text entry method is a channel. And Shannon called this channel a discrete channel with noise. And there are 3 formulas which are key to calculate the throughput of this channel. And all the factors in the formula can be gained from the text entry logs. So after gaining the throughput, to verify the stableness of throughput, we conducted 2 user studies with laptop and smartphone keyboards, where we made users to type in different speed accuracy conditions. And we found that among all the metrics, throughput was the most stable metric.
Okay, the work that you have done are pretty interesting. But this is more like a proposing a presentation, right? So what are you proposing afterward?
Yeah, sure. I'm going to talk about my proposal. So this is the chapter 4, where I'm going to talk about my proposal, all the work. My previous work mostly focused on mobile devices, but most of the concepts and methods can also be utilized in other scenarios. So to extend the previous work, my proposed work is about designing intelligent text entry methods for ubiquitous computing environment. And what is ubiquitous computing? Basically, it means the device is everywhere and computable. We already know that they have different form factors and input modalities. So the question is, can we have a unified yet simple text entry solution that is generalizable across different devices? This brings up to my first proposed work, Type Anywhere. So it's a ubiquitous quotary text entry solution. The envisioned scenario of Type Anywhere is that by wearing a wearable device on both hands, the user can perform quotary style text entry on any surface, just like typing on a keyboard, but without a real one. To implement the interaction, I use a finger-worn device called Tap, which is able to detect finger movements. And by recognizing those tap sequences, I can then decode those into text using neural language models. A benefit of Type Anywhere is that users can just leverage their existing physical keyboard typing skill without learning new interaction. To support text editing, I also designed operations like multi-finger QWERTY gestures for different functions, such as backspace and candidate selection. To translate the tap sequence into text, I trained a decoder based on the BERT neural language model for better incorporating the context. And this is the demonstration of Type Anywhere. So I conducted a user study to evaluate how the technique performs in the real setting. Here I show 2 users' performance from the study where it lasted for 5 days. every day they use Type Anywhere to perform typing on a hard key, on a tabletop. And also on the last day, they perform it on their labs. The upper line here shows their physical keyboard performance, and the lower line shows their lab performance. And we can see that the trend is they are improving their performance in general. And we also found that for this user, the final performance for Type Anywhere even reached nearly to his physical keyboard typing performance. So this showed the feasibility and also low learning barrier of Type Anywhere. A follow-up work is called Type Anywhere 1, where it only used one hand to perform similar interaction. The envisioned scenario is for motor impaired users where they only have one hand. Here you go. One hand available for typing. And the second scenario is for situational impairments where one of our hand is occupied by a task. And the last scenario is just because we are too lazy to use two hands. And the design of Type Anywhere 1 is to mirror the other hand layout. The idea is inspired by previous work where researchers use a half-quartering keyboard and showed that users can benefit from this mirror design using their muscle memories. So basically, if you type a finger on one hand, it will map to the same finger on both hands. However, this significantly increases the ambiguity of the decoding process because there are now double options for decoding. So to solve this ambiguity, I propose 3 directions: improving the modal structure, inventing some easy gesture for candidate selection, or some gesture for hand specification. For example, you specify whether it's right or left hand. To evaluate the technique, I propose similar longitudinal study on both hands, so only for left and only for right hand. And the last proposed work is an accessible text entry method for large touchscreens. It's called Anchor Keyboard. We know that large touchscreens are becoming ubiquitous. So while they have larger space for interaction, they require visual attention and present barriers for blind and low vision users. Current solutions include using an external keyboard, or use Braille keyboard, or use screen reader for on-screen keyboard if you want to type without looking at the keyboard. And the proposed design is to put all the fingers on the screen and only tap the corresponding finger when typing a character. In this way, the screen can figure out which finger is typing using other fingers as anchors. And the user can just type without looking at the keyboard. At the same time, they still use their physical typing skills by performing the same finger-to-key mapping. So they can just start typing without learning. By using some machine learning algorithms, the keyboard can then figure out which key the finger is intended to touch. I promise this will be the last demo.
Keyboard initialized. Delete. A space uppercase A C O B uppercase space uppercase O B O C K space T 0 cancelled. Notepad initialized 0 delete 0 9 0 delete.
Okay. Yeah, so that's an early prototype. Some other extensions of this project could be adding punctuations with gesture input, more text editing options, and also adding emoji input because we love emojis. The timeline proposed is shown in this slide. Starting from spring 2021, I will primarily focus on the Type Anywhere 1 and Anchor Keyboard. Hopefully by then I can start the in-lab user study again. I plan to finish the thesis writing in winter or spring 2022. So combining with all the work, I aim to show that artificial intelligence can enable and improve advanced text input interactions, including the entering and editing of text and the entering of emojis. These interactions in turn warrant new text entry metrics for their evaluation. The expected contributions are threefold: theory, artifact, and empirical findings. For theory, I have the metrics and models for text entry. And for artifact, I have all the intelligent input methods and the proposed work. And for empirical findings, I have studies results related to the emoji usage, and also the proposed work concludes 10-finger typing empirical finding for BOV users. And lastly, I want to spend some time to thank everyone who supported me along the way. I'm here today because all of you. And I want to thank all the names here, Jake, Alexis, Shuming, Leah, James as my community, and all the names below. Abdallah, Stephanie, Adam, Xiaojun, Jacob, Wenzhe, Erin, Rachel, Liang, Chris, Yvette, Scott, Fanwen, Alex, Qisheng, Suning, Toby, Yuying, Alex, Martez, Dichen, Paul, Luke, Millie, Annie, Ether, Jing, Qing, Rolin, Xia, He, Benj, Xuhai, Jackie, Dongbo, Rohan, Xiaoyi, Yang, Yiming, and Mingyuan. That is my proposal, and thank you everyone for listening.
Okay, thank you, Ray. There we go. All right, great. We are right on time. I appreciate you, Ray, keeping to the time frame we discussed. That was great. Let's go ahead and open up for questions. And just for the sake of proceeding, we'll just start with a question from the committee. Is there anyone on the committee who would like to ask a question?
Sure, I can start. Thanks, Ray. It was great to see how all of this has developed. You made it really fun for all of us too. I liked hearing everybody's name at the end. I was kind of curious about the Type Anywhere project. I know that one of the motivations that you talked about was creating innovations that are socially acceptable, and how kind of speaking out loud might not work in a lot of contexts. And I wondered what you found in your preliminary work, or what you think about the social acceptability of wearing that gadget and bringing it into the interaction experience.
Yeah, so basically, like the main focus of Type Anywhere is that we don't need to bring a keyboard anywhere with us, because that's just like tiring. And we need to connect to different devices. And I think for now, the prototype of the device is really big, where it's like very noticeable when you are performing something. But that's more like a prototype. Like in the future, if it's more like a method where once you can recognize the finger movements, you can perform text entry. So for example, in the future, we may have like watch to monitor your finger movements, so that you don't need to wear that awkward like glove or like some extra sensors, where it's more socially acceptable. And as for the interaction, I mentioned that it's more like just typing on a surface. So pretty normal interaction as compared to today, except there is no keyboard. So while I haven't formally investigated that part, I personally think it won't be a like big issue for socially like awkward means.
For the audience, general audience questions, I don't want to be kind of in the middle here. So Ray, do you have the ability to see the participants list? And if so, can you go ahead and call on whoever has their hand up? Unless you'd like me to do that, I'm happy to do
Sure,
that.
I can do that.
Okay, it might just be more direct if you do it.
Okay.
I think there's a hand up.
Hey, Erin.
Hey Ray, thank you. It was fun. I appreciate that you added a few fun entertainment elements for us as well during your presentation. But I also had a question about Type Anywhere, because I was thinking about a guy years ago who I evaluated who just had one hand, and you mentioned that there are existing one-handed keyboards, but the one that he and I ended up using, because he was also missing a couple fingers, was elevated and angled, so it used some three-dimensional space as well. And I was wondering with Type Anywhere, if you're not constrained to a physical keyboard, is it possible to, instead of having that cognitive load and trying to map, remember where all the keyboard, traditional keyboard letters are, to maybe have some sort of three-dimensional gestures that you could use for different letters, which also might be a new cognitive load. But I was just thinking, if you don't have to just always be in this position, but you could maybe move your fingers in different positions up and down in space. So maybe, the letter U, J, M is up, is vertical instead of horizontal on a surface. Is that anything that you thought about, or anything that might be possible?
Yeah, so basically Type Anywhere is, I think the focus is on leveraging existing typing skills for people who already know how to type on the physical keyboard. And I think for the special case where if you want to using gestures or QWERTY, there are also already QWERTY where you type multiple fingers to indicate a character. And that might be less cognitive loading than performing gestures. So yeah, there are definitely diverse design space in this area. But I think for the proposed work, I primarily focus on QWERTY typing because the familiar we are familiar with QWERTY layout.
Back to the committee.
Okay, I can give it a go. So will the committee members will ask questions all at once, or they can return?
So we'll alternate with the general audience for a while so that we can all benefit from hearing each other's questions. But then we will, as a committee, have a private session with Ray to ask questions in that context. I guess that traditionally kind of the private session, maybe we get a little bit more in the weeds or, focused on a particular page or paragraph in his report, in his write-up and things like that, that are maybe a little low level. So this first portion tends to be sometimes the higher level kind of conceptual questions and so forth. It doesn't have to be that way, but it tends to be in practice how it plays out.
So if one committee member has, say, 3 or 4 conceptual questions, the committee member is expected to ask all of them at once or one at a time?
If they relate to each other, kind of part A, part B, feel free to add however many you think Ray can remember. If they're kind of distinct, then maybe just ask one now, and we can certainly come back to you.
Yep. Okay. All right. I'll just start with one. The one is on user learning and habit. So first of all, Ray, you have done a great job in the presentation, also a great job in your PhD projects so far. To me, it's way beyond the usual PhD productivity. So I'm asking a bit tougher or more general questions than usual. So one of them is user habit and learning, and we're seeing in the HCI field plenty of keyboard-related inventions or proposals. But in actual practice, very few of them get adopted. And gesture typing or swipe typing or shape writers probably the only mainstream exception. And this has to do with how difficult it is to change users' habit or behavior, and how much user value their current time and discount kind of future benefit. A simple, you made many more proposals in terms of user behavior change, but One previous example that I've come up with is just change the definition of the shift key. Because in the typewriter days, there's a reason for shift key to be operator before the object. So you specify the case to be typed. Today, with AI and everything else, there's no reason to do that logically, because most of the capitalization can be done automatically. So you only have to change the shift key to be the reverse. And this was actually one of the designs I actually implemented and launched in the initial ShapeWriter app. But we see very little adoption today. So the general question is that with all of this, how have you got a hang of that kind of that trade-off in terms of habit, among learning, and the benefit that we can eventually get, and how you use that to guide your future work?
Oh, that's a big one. Thanks for the question. So yeah, I think the user habit is really a key factor, especially for text entry, because like I said, the quarterly layout has dominated so many years. That's also like my primary motivation for proposing like quarter-like text entry methods for Type Anywhere. I think like for me, the user, I really value the user habit side, where I think if the user habit can be maintained when we are inventing something new, then we better not moving it, because as you said, like the user will not probably adopting a new like a radical change in the design space. So like my current philosophy is, if we can remain the user habit, we'll better do something around that to make that better experience. So if we can remain the typing on quarterly layout experience, we may instead of like designing new layouts, we may focus on how do we design a machine learning technique, or how do we design some interactions to facilitate the users typing in the new design modality. And on the other hand, I think this might not be like a single research project impact, but like I mentioned before, we have numpad keyboard where we have only 12 keys. Then there is like T9 keyboard input method, and once we have the touch screen, there is also a new design space. And currently we have AR, VR. It's kind of like very fundamentally different from the traditional keyboard design space. So I think like only when the I would say the base of the input interaction is different, then there is a new opportunity to design a very like different kind of paradigm for versus the traditional one. But I think like even that's the case, we still have like BlackBerry phone where we have the whole quarterly layout. We have iPhone came out with the quarterly layout. We have people currently doing in VR, AR, they propose like typing in the quarterly in the 3D space. So I cannot like say any opinion for general design, but like for text entry design, because the task is so fundamental that people will stick to their preferred methods unless there is really a like need. Like for example, if you have an impairment or if you are not able to type, you will use speech. So that's my like my method now, like trying to maintain the user's habit as much as I can. Leah, hi.
Hi, yeah, thanks. Lower my hand. So this is kind of following up on Schumann's question and your answer. So you said you're staying in this QWERTY model because of some of these learning issues. So if we are in this QWERTY model, I'm wondering how close you think we are already to optimal text entry input? If we're not, like, what does optimal text entry input look like in this QWERTY model? And if you were to break out of the QWERTY model, then what would optimal manual text entry input look like? I'm just kind of wondering, like, what's the bigger vision there?
So I think, so if you think about it, the QWERTY model or other kind of layout, if people are just doing work on layout, then the the foundation interaction is just press a key. And based on like the like some muscle model, or like we human have a limit on that kind of interaction. So I don't think it's a layout that's constrained us. Like if we are going to think about like more higher or futuristic keyboard, there must be some kind of invention on other modalities. For example, not only typing, or if we are talking about like hand gestures, maybe not only about typing finger one time. So maybe it's more about like voicing or other modalities. Like QWERTY key is already can surpass the typing, the traditional typing interaction. So like in my mind, it's not the layout, but the interaction that's limit that's constrained the performance of text entry.
Any questions from the non-committee members of the meeting today?
Erin.
I have another one if nobody else does. Just what you were saying, Ray, is now making me think about the advantages of eye tracking in conjunction with something like Type Anywhere. Because especially like on the phone, I loved your demonstration. I think we've all had the, you know, the poop instead of pool kind of example. And sometimes because I'm old, I'm not able to even move the cursor exactly to where I want it to go to make a correction, but I can look at it. And just about what you were saying with, you know, multimodal, is there any room, do you think, in the future for having something like that, like integrated into smaller screens? Like having different types of input together to improve accuracy and to decrease stress and fatigue, which I think is the other like qualitative component that I would love to see is how are these different interaction types affecting people's stress levels?
Right. So yeah, like I said, I think the future of text entry, if not like on transcription or like formal tasks, it's really like voice input. Because it's a total different modality, but it's natural. Like we born as someone learn to speak something. So again, voice is also like a very human habit thing. Like we have this habit, so we can use it naturally. Like in the future, like in my vision is like the computer is basically like an ordinary object where it obeys our interaction with the world, rather than we have to adopt some new kind of modality to them. So like if we can just communicate naturally with the device, I think voice is like my goal in the future, maybe. Actually, there are some work combining like eye tracking with typing and voice to make corrections. Like if you look at there, then you say some word, that's a thing you want to correct. So yeah, I think including some multimodal interaction can also benefit from that direction.
I guess I'll go ahead and ask a question. It kind of relates to the previous one, I think. On page 8 of your proposal, Ray, you mentioned that Michel Baudouin-Lafond's models of computers as tools, computers as channels, and computers as partners are different conceptual models for ways that we might interact with or use computers, broadly understood. And you claim that text entry has in the past largely been in the computers as tools category. That, you know, we're just using these techniques and methods we might use that text to communicate or to make notes for ourselves or write a book or whatever we might. Ultimately, it's a computer as tool. And you claim that we're moving more into computers as partners when it comes to adding intelligence in the way that you are to text entry. So my questions actually want to prompt you to reflect about that. If we take for granted that you're right, that we are moving into computers as partners, my question is, how does that actually sit with you? Do we want computers to be partners? It's almost like claiming the computer is our co-author. You know, do we end up putting the computer on the top of our Chi papers because it's a co-author in, you know, our paper? That might sound a little ridiculous. It's meant to, but the point is that there's a very different kind of relationship we have than we have with a tool. If what you claim is correct, one thing to observe it. It's another thing, though, to observe whether you think that's desirable or something to work towards or away from. So I'd just like to ask you to reflect a little bit about that. If you think about computers as partners, as we author things, does that somehow remove our voice or agency in ways that we might not like?
Yeah, right. That's a serious problem. Well, like in my proposal, I phrased it in that way because for some tasks, like my focus, my meaning is for some tasks, if we want to perform, traditionally we have all do it our own. But now there are some assistant from the computer that can ease the process. But I guess I haven't reached to that like higher level, like if we are collaboratively writing a paper or something like that. But yeah, I think that's well, I cannot say whether it's preferable or not, because I think that's definitely a direction happening now, because, you know, like we have Gmail, Smart Compose, we have Smart Reply, and whether the model is doing good or not needs more evaluation. And I would say like the current evaluation, based on my knowledge, is not so diverse. Usually we still stick to the traditional evaluation, like whether that words match to this ground truth words or not. Versus if we are going to evaluate, we might say like the social impact, like are they encouraging people to write more, or is it derived from your original thoughts, or like coherent with your original thoughts? So I think that's definitely need more evaluation. I would say like no matter what kind of technology invented in the future for this kind of as a partner part, we always need kind of, it's important to come up with some metrics or evaluation accompanied with that to further investigate the benefits or the impact. But I personally don't refuse the direction. I think it's very cool. Actually, we have seen many like recent advancements other than text entry. Like if you are going to edit, make a picture, or like even in the PowerPoint, there are suggestions on the style. Like if you make a page, there are like suggested styles you want to make. So I would say that's already kind of like collaboration. But still, as long as the decision power is in our hands, I don't think it will be too problematic. Like as long as you have to click that to input your message, rather than you send and it automatically change the style for you. I think that's really like a no thing.
Okay, thanks. At this point, I think it's fair to say we can go from the committee or the audience. Everybody's getting a chance. So raise your hand if you have a question, and Ray can call on. Schumann, I see you unmuted. Did you want to follow?
Yeah. If you want to go to the audience, then that's fine. But if you want to go to the committee member, then I want to follow up.
Yeah, that's okay. I don't see a digital hand raised. So why don't you go ahead for the sake of proceeding efficiently here?
Okay, so it's related to both of my first question, but to more of a degree, the current discussion that Jake raised, namely the relationship between AI and HCI, or more the tool or the tooling side of HCI. So obviously, it's questionable. It's desirable if the computer become kind of a co-author that, in the sense of attention, in the sense of introducing its own intentions or purposes or goals. That's questionable, and it's also whether that's possible is to be determined. But even at the current level, whenever you use a language model, which practically any text input method would require one, with exceptions, but the mainstream ones and the state of art, it does require a language model, which already conveys certain assistance. So the question is that how do we deal with that side that comes from AI that's still along with the intention of the user, or on the information side, which you use information theory, in that sense, that the information should still come from the user, but the AI is about reducing the noise and reducing the ambiguity. So in that regard, there are two kinds of questions comes up that related to your current work and current presentation. One is the cost of the false positives, like the smart correction techniques. We know they rely on some sort of detection of what's likely to be wrong, and then there will be precision recall problems. There will be false positives, and how in general, what general principles you can derive from your current work in terms of guiding that, or even in terms of making a judgment call that is, well, yeah, at this F1 or FN score, it might be a good idea to explore this, but overall it's not worth trying because the false positive cost is too high. The other side related is that you can always present these things without committing to it. And then it requires user either like in your delayed decoding ideas, or longer span like in phrase flow, or even error correction in the sense only highlighting the errors traditionally through underlying or background color techniques. That still introduces attention cost. And what are the fundamental trade-offs in here? Which is frankly, it's very hard to get a grasp on, because it relates to the first my first question, that is how much user would willing to be learn these new signifiers. And then ultimately there's an equation in terms of user benefit that simply by measuring time or error on a given data set or given method, it may not reflect that deeper attentional or interactive cost on the part of the user. So I feel you already have, your projects already touched on some of these, but how they can be getting to the next level to become more generalizable principles for future work.
Yeah, like I think most of my current experience is scattered. Like I haven't built up a coherent theme on how to evaluate the user attention. What I can say for now is, for designs, always make the system transparent. Like in our phrase flow project, always show the real-time decoding results will make the user confident. Like on the fundamental level, it's related to the user trust, like whether the user is trusting this system or not. If I'm trusting you, I won't pay too much attention. And if I'm not, I might just, like, even you are doing great, I will just pay continuous attention every time I perform. So how say, like, one thing is make transparent system. The other thing is always make fallback strategy. Like if there's some error happen, you should make it easy for the user to recover rather than stick to it. So yeah, that's my 2 cents on the attention level. But I do see, like, if we want to measure it rigorously, we can, besides asking the user their subjective metrics, I think paper or studies doing like the what's that the like using sensors to measure their eye, like where they focus during typing. If they are focused more on the text itself, then it means they are trusting the keyboard more. Versus if they are like flowing here and there, there are definitely some distracting factors going on. So I don't think it can be directly measured for the user affordance or like the user attention. But with some objective sensing techniques, I think we can just interpret. And it's also like situational, like it's for typing, you might measure the eye movement, but for, like voice, like if you are measuring the attention when you are driving using a voice system, that might require you to measure some other, like whether your driving trajectory is smooth or not, or like whether you are successing in like giving way to other pedestrians. So I think it's very situational, like context sensitive for attention. But I definitely don't think only subjective measure is the key to merit. There are like other objective tests. But for now, I don't have a like coherent theme on how to derive that.